There we go. So just a quick announcement for AICHE. AICHE stands for the American Institute of Chemical Engineers, and we have a student chapter here on campus that does a bunch of cool different projects and things. They have a workshop coming up that they've asked me to invite you to. That workshop is for Python. I can't actually highlight on that. Let's use red instead. It's for Python. And so if you're interested in that, they're going to have their Python workshop on Tuesday, April 14th, which I just checked my calendar here on the bottom left. That is tomorrow. And it'll be tomorrow evening via Zoom. And so I'm going to copy paste the link here in a minute so you don't have to try to scribble that down really quick. Python's a great language. So obviously we use MATLAB in this class a lot. You can do a lot of interesting things with Python too. And I think this would be an interesting opportunity if you've thought about using Python, but haven't had an opportunity to do so. Just as a keynote on here, you don't need to be in AICHE in order to come to the workshop. So you can just show up if you want to, but please RSVP. So the RSVP link is here, but I'm going to actually post that in chat right now. So let's send this out to everybody in chat. If you're interested, I just posted the link in chat, and so you're welcome to sign up there for the AICHE Python workshop coming up tomorrow evening. I'll also post that same information on our Canvas page, just right up at the top of the Canvas page, at least until tomorrow, when the actual workshop is there. Just a couple of notes for where we are in the class. Just a couple of general reminders here. Oh, I can't draw with that. So two things are due today. So your second review quiz is due today, as well as the first homework. And both of these are due at 11 p.m. And so the homework is going to be through Gradescope, just like it normally has been. And the quiz is going to be through Canvas, very similar to what the first quiz looked like. I'm zoomed in a little bit. We'll zoom out a little bit. I'm going to zoom my camera out. It just looks like it's a little bit close. It's not that I don't like you and I don't want you to be right in my face, but you're kind of in my face right now. Okay, I actually like it better that way. Yeah, good enough. Okay, you can stay there. That's fine for now. So both of those are due today. The other thing that's not due today, but you should keep in mind because it will be due eventually, is the first project has been posted, which is your first midterm project. We have already covered all the content that we need for that. So all content covered. That project is the first part of the report that you're going to complete. It'll kind of go through, I got to take this off. It's itchy for a minute. It'll go through most of the sections of what a normal report would look like, except that it'll come in chunks, right? So your initial project will look like the sort of the introduction of the report, as well as some of the initial calculations that you would have to do. But nothing in this initial project will actually require like a write-up in that sense. And so you'll just be developing some of the initial functions that you'll need for the next few parts. Most of the work on that one in terms of how does it directly relate to this class are going to come down to net rates, right? So the big chunk of that that's at least due to calculations is going to be the calculation of net rates. And so you're going to be looking at a water purification treatment or water treatment system, which is a bioreactor. And so those net rates are actually going to look very similar to problem 1. It should be 1.11, right? The one that you're looking at in this particular homework where you're writing net rates for just a generic bioreactor system on there. Those are actually taken as an example that's very similar to the one that you're going to look at in the project. The due date of the project, I don't remember off the top of my head, but it's posted on Canvas. Homework 2 is available. The stuff that we're going to do today, like it said, it's due on the 24th. Thank you, April 24th. So you've still got a little while to work on the project. but you would want to look at it, right? You don't wait till the last minute to try to do the project. Generally, my suggestions with the homework, you should be looking at about maybe one problem a day. There are fewer assignments now. That first homework, it was almost 2 weeks long, which is a pretty long one. And that's why there were more problems on there. But if you're on a pace of about maybe a problem a day, maybe some days you get motivated and you do 2 problems in the day, you'll more or less keep up pace with what we're after in here. And then, so as I had mentioned in the outline, the first few problems on that homework, you'll be able to cover with the material that we're going to introduce today. Sorry, I'm just double checking that we are in fact recording because I have made that one. Yes, if you tried to do all of homework 1 yesterday, I can understand being exhausted today. That's a lot of homework to do in one day. Okay, so our topic for today, we are finally going to introduce something, what I want to call new. So the material that we've had up until now, if you look at the first few weeks with, or the first few days with thermodynamics, it was supposed to be kind of a review, but I can also understand that it didn't really feel like a review, right? It probably felt like I have seen things like this before, and now I kind of have to learn it all over again with, you know, some variations to the notation that we use or something like that. So I can imagine that that felt new. The rate stuff probably also felt a little bit new, but at the same time, it probably felt somewhat familiar with what you would have done back in chemistry class. But again, you know, the syntax is probably different enough that it felt like it was kind of a brand new topic. This is the first topic where we don't really have some kind of prior experience with it to draw on. So in that sense, it is new. On the other hand, it draws very heavily on the first 2 things that we did, the thermo and the rate laws, and very heavily on the stuff from CENG 100, right? Material and energy balances. And so in that sense, there will again be those things that kind of feel like, yeah, I've seen this before, but I've never done it quite like that. And then obviously we're trying to get you up to speed where you say like, yeah, this seems familiar, right? I've done things like this, and I'm confident that I can keep doing this on a new reactor. And so the new reactor that we've got is abbreviated as a CSTR, which is a continuously stirred tank reactor. And I will very rarely actually say continuously stirred tank reactor because it's kind of a mouthful. We just call them a CSTR. There are other names for them that you might come across if you're doing literature. Sometimes they're just called tank reactors. Sometimes they're just called stirred tank reactors, whatever. They all pretty much mean the same thing. So let's look at a quick sketch, or not even look at it. Let's draw one real quick. So if we imagine our tank reactor to look something like this, the ones that we're going to start off for now are going to be liquids. So the only things that we're going to deal with for the first 2-3 weeks, week or so of this material is all liquid. And so that's why I draw it this way. It looks like there's a little liquid sitting inside of it. There is usually a stirring mechanism that sits down inside of there, which I usually draw like this. Give it a little couple of vibration noises there. So that is going to be key to one of the assumptions that we make in a moment, but there's usually some kind of a mixer down in there. Maybe it's a paddle mixer, or it's kind of like a screw or something like that. It can look exactly like the propeller on the back of a boat. We just call them impellers instead of propellers, if that's what you're doing. Usually there's 1, possibly 2 inlets to the system. Actually, let's move that up a little bit. Almost every system that we would deal with in here is only going to have a single inlet, because a lot of reactors are designed to only have a single inlet and a single outlet, because it's hard enough to manage the temperature profile and the mixing inside of there if you don't have a bunch of ports, sort of, you know, holes drilled all over in your reactor and stuff coming in through there. So a lot of times we're going to be dealing with a single inlet and a single outlet, because that's how a fair number of reactors are actually designed. Coming out of the reactor is usually 1 stream, like this. And I draw it the way that I drew it here because the volume inside of the reactor is usually constant. So the volume here is usually constant. And we're going to have two different V's that we have to deal with. And so I have gone out of my way to put these little caps on my V, the little horizontal lines up on the top, and that is to distinguish it from a different V that we're going to introduce here in a moment. So this V is supposed to be capital V, and that's how we will always refer to the volume of our reactor with a capital V that sits on top of there. So we have a couple of different streams, obviously labeled right here. We've got some inlet coming in and some outlet coming out. This one coming in is what we refer to as our process inlet. So that's the stuff that's going to undergo the chemical reaction. Similarly, the one coming out over here is our process outlet. That is the stuff that has gone under chemical reaction or participated in the chemical reaction. This is to distinguish it from a different type of fluid that can also be used in the system. And so if you imagine like a case that sits around the reactor, there can be additional fluid that goes in through here and comes out through here. And so it kind of circulates around the outside of the reactor until it comes out over here. This is what we refer to as our utility. So on the one side, it's a utility inlet, and on the other side, it's a utility outlet. Utilities are things like cold water or steam, right? Or hot oil or something like that. The purpose of a utility is to promote heat transfer from the inside of the reactor to whatever that outside part happens to be. This whole structure that we're referring to here, I guess I might as well keep that in red. This is called the jacket. Jacket is a type of system that we call a heat exchanger. And so it's a way for us to, if we need to heat the reaction up, we could, pump steam or something like that through our utility. The hot steam is separated from the reactor by usually a metal wall, like a copper wall, stainless steel wall, something like that. And the energy can transfer from the steam in the jacket into the process fluid. The reverse is also very possible. We use this a lot where the reactor itself is undergoing a chemical reaction. They're very often exothermic, so they're giving off energy, and we need to draw that energy out of the system. And so we might use like a cold water or something like that to draw that energy out. So the utility is something that we come up with a lot, but the key point of the utility is that it doesn't actually mix with the stuff inside of the reactor, right? It's its own separate streams, and we're going to have to deal with those later. The mixer that's here can occasionally inject shaft work. So that's W sub S, which should look very similar to the terminology that we used in thermo or in material and energy balances. It is possible for that thing to inject a significant amount of shaft work into the system, although as we'll see when we eventually get to the energy balance, for everything that we're looking at the moment, it's very tiny. We usually don't worry too much about the shaft work. In order to develop those conservation equations, right, the material balance and the energy balance, we always have to draw a control volume. Remember, we don't just write a random material balance on nothing, right? We have to be writing that material balance around a particular volume of space of the universe. And so when we're dealing with a CSTR, the control volume that we want is all of the liquid that's inside of there. Technically, the mixer itself is not part of that control volume, but it's too much hassle to draw it as though it's not. And so this is the control volume that we're interested in. We don't really have to come back to that control volume a lot. It's just what we use to develop our material and our energy balances. So if we take this view and sort of simplify it a little bit, right? This is the reactor that we're referring to the majority, or I guess it's over there, isn't it? If you're watching the video and my face is on the right and the video is on the left, this is the system that we're going to deal with most often, but that's a lot of drawing. And as engineers, we are generally pretty lazy at drawing. So we're not going to draw it like that every single time. We're just going to give it the classic little box that we always do. It's kind of hard to tell the difference between an equilibrium reactor and a CSTR if we always draw it as a box, but you'll always know what the reactor is supposed to be. So occasionally we might put a mixer on there just to remind us that it's a CSTR, but it's not going to be there all the time. We've still got some inlets and some outlets. I have not drawn the utilities, right? So this drawing, no utilities yet. We're just worried about the process stream. We'll come to the utilities later. The utilities don't enter into the system until we have an energy balance to deal with. So we've still got a little bit of time with that. The things coming into and out of the system follow the same types of abbreviations that we saw before. Things like inlet molar flow rates and temperature. So the subscript 0 there reminds us that this is on the inlet. And similarly, the things coming out over here are the same variables, but without the zeros as the subscript. We add 2 new variables that we've actually already been introduced to one of them, but we're finally going to learn how are these actually related to everything else. One of those is what we call a concentration, C sub I. So the concentration coming in is C sub I 0, and the concentration coming out is the outlet concentration. These are molar concentrations. And so they're going to be things like moles per volume. Maybe it'll be kilomoles per liter. It's probably more often moles per liter, or maybe kilomoles per cubic meter, whatever. They're going to look like a mole per volume, both of those. The other is the new symbol that I said we're going to try to be careful with in terms of our exactly how we draw it. The lowercase v is a volumetric flow rate. And so a volumetric flow rate will have units of things like volume per time. So some very common ones that we would see here are things like liters per second, maybe a cubic meter per hour, something like that. That's our volumetric flow rate. This one is the one where I wanted to be careful to say that this is lowercase v, as opposed to the uppercase V for volume. So the uppercase V is always volume, and that's referring to the size of our reactor that contains all of the stuff that we want. The lowercase v is a volumetric flow rate. It's just sort of the difficulty that we're in, that we only have 26 letters in the alphabet, 52 if you make some of them caps and some of them lowercase. And unfortunately, some of the caps and some of the lowercase look the same, right? C's and V's and that sort of stuff look really similar when they're uppercase and lowercase. For the most part, the lowercase v that we're going to deal with generally always has a subscript 0 on it for a reason that we'll introduce here in a moment. But ultimately, you just have to go by context to decide what it is we're actually referring to. They both show up in fairly usual places, and so that helps, right? It gives us the ability to figure out from context which one we're talking about. There's a key assumption of a CSTR, and it's the one that we're going to make every time we have to deal with a CSTR, and that is what we call the well-mixed approximation. So if we scroll up a little bit, the well-mixed approximation can be understood by this mixer that's sitting in here. So this mixer is usually providing a lot of agitation. And in fact, one of the things that we do when we're trying to design these reactors, if we actually want to build one, or if you ever happen to go out and buy one, is add all sorts of clever little things in there that really make the mixing very, very effective. We don't want there to be pockets of this reactor in one place or another where the concentration of the species is different. We want the whole thing to be uniform and reacting uniformly. So we might add like baffles to the side. Maybe we have multiple mixers. Maybe we have multiple layers to our mixers or something like that. All of which are intended to make the contents of the reactor itself as absolutely close to uniform as we can get it. If you come back for graduate study, you'll learn some of the basic models that we have for what happens if it's not well mixed. But everything we're going to do in here is a well mixed approximation. And trust me, it gets complicated enough with the well mixed approximation that we're going to have plenty to deal with the well mixed approximation. So the well mixed approximation says that the concentration of species I, so C sub I, within the reactor control volume, so within the reactor CV, is uniform. And that's the key portion of the well-mixed approximation, is it's uniform, right? Everywhere inside of the reactor, the concentration is uniform. If it's uniform everywhere, and you consider this little portion of the tank, right where the outlet is, there's a little bit of fluid from the main part of the tank that's coming out and leaving our control volume. Whatever that is the same as everything that it is inside of the tank, right? We mixed everything up and then we just pulled out a little bit as our outlet. And so the implication of the well-mixed approximation is that whatever's inside the tank is exactly the same as what we're pulling out. It has exactly the same compositions. So the impact of the well-mixed approximation is that therefore the concentration of any species I within the reactor has to be equal to the concentration of species I in the outlet. And that's going to be really good because of when we write our material balance. We're going to need that assumption in order to actually allow us to calculate anything with our material balance. That material balance has not changed. It's the great thing about a conservation equation. They don't change. So it's still in minus out plus generation minus consumption is equal to our accumulation. Not surprisingly, or I suppose maybe not surprisingly, we're going to operate at steady state. So we're not going to have to worry about accumulation. No, so there was a question in the chat. There's no reaction, just mixing. No, there definitely is a reaction within the control volume, but not in our outlet streams. And so let's write both of these really quick. So we'll have 0. Our general term for any species coming in is n sub I 0. Whatever's coming out is n sub I. Those are exactly the same ni and ni0 that we were dealing with last week. This part, the generation and consumption, we're dealing with the control volume, right? We're writing this over our reactor control volume. If the concentrations of the species are constant, then is the reaction in equilibrium? No, those are two different things. The reaction would be in equilibrium when the concentrations are given by their equilibrium concentrations, but just because they're constant doesn't mean that they're in equilibrium. For example, if you turn off the reactor, the reaction or the concentrations will be the same as the inlet, which is definitely not at equilibrium. So no, just because they're constant doesn't mean that they're at equilibrium. This term for the generation and consumption used to be the moles of I times the extent of reaction. So this is what we would call that term in CENG 100. That is still valid. There's nothing wrong with that. The limitation of that is that it gives you no idea about how fast the reaction is occurring. So if you recall from CENG 100, we never brought up these rates in CENG 100, and therefore we had no way to estimate, for example, how big is the reactor, or if we want to achieve a particular conversion, what's the volume of that corresponding reactor. The reverse was also something that we never looked at. If we are given a particular size reactor, what is the conversion of that reactor? We are not able to answer those questions if we're only using extent of reaction. And that's where the brand new thing of sort of the reason that we have this course is because we have a better way to do that will answer those questions for us. And so the way to do that is through our constant or our rate of reaction, R sub I, times the volume, right? So R sub I times V is, or I should say has, the same units as the stoichiometric coefficient times squiggle, which is a mole per time, right? The same units as N sub I as well. The key point though is because our material balance was written over the reactor control volume, this is the rate of reaction here within the control volume, right? This is within the reactor. that's problematic because we usually don't have some way to sort of stick stuff down inside of the reactor and get samples out. Or if we do, it's kind of a pain in the neck and we don't want to reach down inside of that reactor. And so because our R sub I is a function of our concentrations, right? Remember, these are things like K times Ca, or maybe it was K times Ca squared, or K Ca minus Cb over Kc, right? All of those Cas were referring to the concentrations inside the reactor, which we don't really have access to. We don't often know what those concentrations are directly inside the reactor. And this is why the well-mixed approximation is so important. This gives us the ability to approximate the rate of the reaction inside of the reactor based only on what's coming out of the reactor. And so our R sub I here, if we use the well-mixed approximation, if it's well-mixed, then this R sub I within the control volume simply becomes the R sub I in the outlet, right? I can say now that R sub I, where'd my pen go? Is a function of the concentrations coming out of the reactor. Which is great because that's we're a lot more interested in that stuff, right? That's our product stream. That's the stuff coming out of our reactor. But also, if we ever actually need to measure something, it's a lot easier to just divert a little bit of that outlet flow into like a bucket or something like that than it is to reach down inside this reactor, right? Imagine there's that stirrer is running. We've usually got a lid over the whole thing, right? And we don't want to have to reach down in there and bring it out. We can actually just sample the outlet, and that's a lot easier. In terms of mathematical convenience, it just so happens that's what we're interested in, right? The outlet stuff. So our material balance, the one that we're going to use pretty much all the time, in fact, we'll always come back to this, will just be written as R sub I times V, right? And the assumption of this, the implication of this material balance is that the rate R sub I can be calculated based on the outlet molar concentrations of all of the species. And so this becomes our CSTR material balance. And so the other key thing of our material balance is that we get 1 per species. So if we have species A, B, and C, then we'll have one of these material balances for every single one of those species. Some of the terms, let's explore some of these terms in a little bit greater detail. The two that are easier, I want to say easier, not that they are necessarily easy, are these N sub i's. So the molar flow rate is related to the molar concentration and the volumetric flow rate by a pretty straightforward expression, which is N sub I is equal to C sub I times V. We're going to use that expression a lot. That is our primary way of converting between the moles that we need in the actual material balance and the information that is typically provided to us, which are concentrations and volumetric flow rates. Can you show the material above for a second? Sure. We can keep working. And so we're going to use that relationship a lot. This is going to come up a fair amount. Remember that the V that's sitting here is the volumetric flow rate. So that'll be things like, you know, liters per second or something along those lines. I gotta scroll down a little bit, Andy, sorry about that. If we take the sum, let's keep this in red since we're dealing with moles of I. If we take the sum of all molar flow rate, all molar flow rates N sub I, that's the same parameter that we saw a moment ago, which is N sub T. That was in the previous material that we covered. So if we sum them all up, we just get molar flow rates of T. If we divide both of these by the volumetric flow rate, let me straighten this out. Sorry, I'm going to rewrite it all in a minute. I don't know why I'm writing sideways. If we say the sum of N sub I over V, we knew that N sub I summed up is N sub T, so let's divide both of those by V. This term is called the total concentration. And that is exactly the same as if you just sum up all of the individual concentrations. So if we ever, that's the C sub t that we saw when we were dealing with the equilibrium constants, and this is how we would calculate it. And so we can use an expression something like this. Another key assumption that we have for liquids, and we're going to revisit this assumption when we get off of liquids, the inlet volumetric flow rate V0 is equal to the outlet volumetric flow rate V. And so that's helpful because it allows us to only have to specify one parameter in the system. We can just say, you know, the feed is being provided at 6 liters per second or 10 liters per hour or something like that. And we know the rate at which it's coming out is pretty close to the same. That's not a terrible approximation for liquids. But we will relax that approximation when we get to gases because that's a little bit harder. Or I should say, it's not quite as accurate for gases. This R sub I comes from chapter 3. So that's why we were introducing things in chapter 3. And generally, R sub I is equal to the sum of the stoichiometric coefficients times the rate of reaction for each reaction. Right, so that was part of what we did in chapter 3. We also looked at this R sub j, and so we found out for elementary rate laws, or elementary rates, R sub j looks like things like K, actually I'm going to get rid of the subscripts there. R might be something like KCA, maybe it's KCA squared, whatever. If it's reversible, then it often looks something like KCA CB over KC, right? This was also chapter 3. And now finally, this KC, so I'm trying to link everything that we've done and so that you can see how these things are related. K sub C is going to be a function of K sub A, right? And now we're finally back to the stuff that we started with in chapter 2. Oops, that's supposed to be blue. And so that's supposed to be sort of a map of how has everything that we've done up until now been leading up to this one material balance equation, or I should say these multiple material balance equations, because again, you have one per species. And so if you ever need more than one, you can always come back and write it again and again for more than one species. You just write a new equation and you get a new material balance. So you have an extra equation if you have more unknowns than you have equations to solve for. So chapter 2 feeds into reversible rate laws, which is chapter 3, and then chapter 3 feeds into chapter 4 because now we finally got a model of our reactor which requires those rates. And those rates, if they are reversible, require the things that we used in chapter 2. And so this is now sort of bringing all of these things together. If you don't have a reversible, oops, what's my pen doing down there? If you don't have a reversible rate or a reversible reaction, then there won't be any dependence on the thermo stuff that we have learned up until here. Not that you won't need it, because eventually we'll have material balances that will require it. But the dependence on K sub A will only come up whenever we have a reversible reaction. And it will come up through the rate, and the rate will go into our material balance. So this equation, the material balance that we've got, let me even erase it just so that I can highlight it again. And I know John doesn't like the erasing, John, or the highlighting. John, you should try making the highlighter bigger like you mentioned before. Yeah, it's really great. It's very satisfying. That equation is the one we're going to come back to over and over and over again. So when you're doing the homeworks in homework 2, I suggest you start with this expression, right? Write that out and then see how you have to feed in all the various bits of information into that single equation until you get down to one equation with one unknown. Or if you have more than one, maybe 2 equations with 2 unknowns or something like that. But try to keep that equation right at the front of your mind because it's the one that will be able to solve all of the CSTR problems. Everything that we do from here on out for CSTRs in terms of a material balance always rely on that particular equation. And this is why I wrote it at the beginning of the chapter, even before we had even derived it, right? If you need to know where to get started, flip right to the front of chapter 4. That's the material balance. There is no problem in our CSTR world that cannot be solved by that material balance. So it's very general, and that makes it pretty powerful, but it can be a little bit intimidating to use because you've got lots and lots of different parts to put together for it. So that said, let's look at a simple example of just how we can throw all of this material together. And also what some of the problem statements might look like. So we've got our reactor. Got an inlet and an outlet on there. And so the stuff that we know are the Ca0. So this is what we would call the inlet molar concentration of C sub A. And this is going to be equal to 2 moles per liter. Right, it's always going to be an amount per volume. Maybe it's kilomoles per cubic meter or something like that. Who knows? The inlet volumetric flow rate is V0. And so this one, again, is some kind of a volume per time. So here we're just saying it's 4 liters per second. It could be gallons per minute or something else. We don't know. That's our inlet stream. The CSTR that we've got here will have the reaction A goes to B. Actually, I can move this up. Let's move this aside a little bit, just so we've got a little bit more room to work with here. There we go. So our inlet goes in through here. The reaction that's going to occur inside of here will be A goes to B. We will often assume that the reaction is elementary, and so our rate law will just be some kind of a number, like 0.2. I know it's going to have units of inverse seconds just because I've dealt with these a lot, and I wrote it up before class. But you'll eventually be able to be familiar enough with the way the reactions look like, what the reactions look like, and what their corresponding rates look like to know roughly what the units on K would be. But they're virtually without fail given to you. The volume of our reactor, we don't know that. That's what we're going to try to figure out. So we'll just highlight that. And then our outlet over here. We're not given any information about that. The only other thing that we're given is sort of what we would call the volume or the problem statement itself. What is the volume for 50% conversion of A? And that's a fundamentally new type of calculation, right? Look back through everything that you did in material balances, look through everything you did in thermo. We never had a way to say, how big does this thing need to be? And that's really important, right? It doesn't matter if you're working in industry or you're working in academia or you're working in a production facility or you're working in a water treatment plant or you're working on, whatever it is you're trying to do. If you're designing a reactor, you need to know how big the thing is, right? If it's small enough to fit on the size of a desk or in a room, or it needs its own building, or like what we're going to see on the project is it itself is the size of a large building. Now, it's never been a question that we've been able to answer before. And that's what we can now answer, is how big does this need to be? And so to answer that, we're always going to go back to the material balance first, which will be N sub A minus N sub A 0 minus R sub A times V. Right, and so this is equation 4.1. For no reason other than that's just the way that I chose to write it, the signs were swapped with what I wrote above, right? If you multiply the left and the right-hand sides of that equation by -1, you get the same thing. So that's why, if you were tracking along, it looks slightly different. It was just multiplied by -1. So if we look at each one of these, let's start with the rate, because usually the rate is, let's do the other ones first, because rates are usually easier. These are usually easier. So let's start off with the easier ones first. N sub A, we know will be equal to C sub A times V. because that's the definition of a molar flow rate. And C sub A times V will be the same as C sub A times V0. The reason that we know that is because it's a liquid. And so these two are equal because it's a liquid. Specifically the V's, right? The V of going out versus the V going in are the same because we have a liquid. Let me improve my little line here. These are equal because they're a liquid. If we look at what's coming in, the moles of A coming in, our concentration coming in times the volumetric flow rate coming in, which was given to us as 2 moles per liter and 4 liters per second. So our molar flow rate has units that we would expect, which is 8 moles per second. Right? That's a pretty good thing because that's what we're after. And now let's deal with the rate. Right? The rate is usually the reason why the problem becomes complicated. It's usually complicated. So R sub A, this is assuming it's an elementary rate law, will be equal to the stoichiometric coefficient of A times the rate of the reaction. So the stoichiometric coefficient of A is -1, and the rate here would be Kca. And that's the part that you're going to practice. Why is equation 4.1 set to equal to 0? Only because I chose to do that. I put everything on one side. I write it like that because that's how we need it in root finding form. But you could also rearrange it so it looks more like out is equal to in plus change, and that would be fine. I write it that way because we need it for root finding form a lot. And so it's more convenient that way. We're going to rewrite it in another class. So this is equal to minus K. C sub A is equal to N sub A over V, right? And that just comes from our definition of concentration. And so this will be equal to minus K N sub A divided by V0. Why divided by V0? Because again, it's a liquid. So V is going to be equal to V0. And I'm doing that every step. I'm showing every step of that calculation because eventually when we come to gases, that will no longer be the case. And we will no longer have the ability to say V is equal to V0. And so I'm pointing out every time we do it here so that it looks more obvious to you. We also need to know N sub A. We have a process specification, right? Our process specification is that X sub A is equal to 0.5 because we have 50% conversion of A. And so this is equal to 1 minus N sub A over N sub A 0. From this, we can find that N sub A is equal to N sub A 0 times 1 minus XA, which is a half times NA 0, which is 4 moles per second. If we wanted to know C sub A, oops, we could write C sub A is equal to N sub A over V. That's its definition. Because it's a liquid, we can write N sub A over V0 is 4 moles per second divided by, what was our inlet volumetric flow rate? Our inlet volumetric flow rate was 4 liters per second. Four liters per second. And so we're left with 1 mole per liter. And now we can substitute all of this stuff back into our material balance, right? So we're going to have our C sub A here, which we just calculated. We will know what V0 is. And in fact, the product of these is N sub A, which we just calculated. We also calculated, or sorry, we used our definition of CA0 and NA0's relationship to calculate that NA0 is 8. And then we just showed what R sub A is. And so our only unknown that's left is going to be V. And so let's substitute each one of those in there. So if we go back to our material balance, it'll be 0 is equal to N sub A. And if I scroll up, N sub A is 4. And then it'll be subtracting off whatever the inlet was, which is 8. And then minus R sub A times V. So minus a quantity of minus K Ca times V. The negative signs and things like that get a little bit tricky, so I tend to leave them around until I'm quite sure of where they go. So this will end up being plus. Our rate constant was 0.02. Our concentration of A was 1 mole per liter. These units, by the way, excuse me, of K are 1 per second, or V inverse seconds. All of that times V. And so now we are left with one equation and one unknown, right? We've got a single V over here. Was it 0.2? I thought it was 0.02. Yeah, it's 0.02. Thank you, though. We don't just randomly change units, so thank you for checking on it. If I did the math here correctly, and I do not always do it, we can rearrange for this and find out that V is equal to 100 liters. That seems like kind of anticlimactic, but like that's huge, right? This is telling us how expensive the reactor is. It's telling us whether or not we can afford it. It's telling us whether or not it fits in a small room or a big room, or it is the entire building or something like that. This is so important to know how big a reactor is. It tells us whether or not something is feasible, or at least it's a very important piece of information about how feasible something can be. The reverse can also be true, right? If we already have a reactor and we want to find out whether or not we can actually produce something, maybe that's good enough, maybe it's not. Oh yeah, you're right, sorry, 200 liters. See, told you I messed up. 200 liters. So once we have that number, if we already have, for example, a reactor, we want to know whether or not we can effectively, purify a stream with that reactor, or if we can effectively produce something else with that reactor. We have to be able to do this sort of a calculation, and we've never been able to do it before because we've never tried to put these rates inside of each other, or inside of a material balance. And so that's the big thing that we're dealing with here, right? The complications to this always come back to how easy was it to come up with this sort of stuff, right? The math that I've shown here. Most of the time, the complication is because the rates end up looking kind of nasty, but it can just vary, right? It could be different things. And so that's where we are. This basic process is the one that you're going to follow for the first few homework problems. And that's why I said you'd be able to at least approach those problems. There's nothing new that we're going to do for the next few days that would make those problems any different. We're just going to see different ways to solve this. For example, how could I do it in MATLAB so I don't make a stupid mistake like forgetting that 4 divided by 0.02 is 200 instead of 100? It happens. We're going to see a couple of different ways in MATLAB that maybe we don't have to make those mistakes quite as often. But presumably, you should be able to do that better than I can, evidently. Because it is, at least for some of these, it'll look something like this. And then we're just going to look at variations of this as we go. So we're up to, it's actually 3:51, so I want to make sure I don't talk any more than that. However, as usual, I'm happy to sit around for a few minutes, so I'll hang out till about 4. If anybody's got any questions, I'm happy to answer them. I will post this, and I will post the AICHE stuff. So I'm done introducing new material. If you have any questions or anything, please let me know. I'll hang out till about 4. We'll throw some of that introductory music on that we had a few minutes ago. Thanks all. Stay safe out there. You're welcome, Michelle. So there's a couple of questions in chat, which, by the way, throw a no in chat if the music is too loud. If it's too loud, I'll turn it down if you can't hear over me. Or sorry, yes, put the no in there if you would like me to turn the music down, and I will turn the music down. Sorry, I wasn't clear on how I said that. There's a couple of questions. Could we do fsolve in a loop? So there's actually two questions in chat. Can I do fsolve in a loop? And then there's another one, I'm having trouble using fsolve with an array. Both of those are, it sounds like those problems are headed in the right direction. And the solution for that is, I believe, example 1.8 in your book. So I'll pull up the book real quick here. Okay, so in the book, if you go to section, let's see here, 1.7, there's an example. 1.6 shows you how to set up fsolve to accept an additional input argument. But the key one that I think you'll be more interested in is example 1.7. 1.7 is doing almost exactly what you need to do for one of the homework problems, which is how do I put fsolve inside of a for loop and solve it for a bunch of different temperatures. And so this solution script that I've got for example 1.7 is almost exactly what you need to do. The only difference between what you'll have in your homework and what I've got here is your temperature range will be different and your function will be different. I suppose your initial guess will be different as well. If you want to set it up in terms of something other than X, that's also fine. But this is the structure that I would suggest for that problem where I asked you to plot the solution as a function of temperature. It's that one. There was a question from lecture, was the conversion as 0.05 given, or did I decide on that? I decided to give you that. So it was known ahead of time. You're welcome, Andy. The big V stands for control, stands for the volume of what part of the reactor. It actually stands, if you want to be very specific about it, it stands for the amount of volume, the volume of liquid inside the reactor. Usually we just take that as the volume of the reactor. Technically it's slightly different, right? The stir rod sits down inside of there and takes up some space, but who cares, right? It's not very much. So the big V stands for the volume of stuff inside the reactor. Generally, we just call that the volume of the reactor. In the past, we've used N with a dot on top for molar flow rate, and in this one, it's just plain old N. Yes, that's how I'm going to use that syntax going forward, because we're never going to look at a system where we don't have a flow. Everything's a flow in here. So I dropped the dot because it's there all the time. There's a question in chat too about how do we know how many moles are reacted in each reaction for problem 7. Let me switch back over to my notes here real quick. What I would suggest you do for that one, oops, it's going to be really hard to write it like that, is make your stoichiometric table. So if you remember a few examples from CENG 100, when we had 2 reactions, we would have 2 sets of stoichiometry, right? We'd have A, B, and C. Maybe it was -1 and -1. Maybe this one was 1 and 0, and maybe this one was 0 and 1. We would still have the amount of moles coming in, and then when we wrote the amount of moles coming out, it would be in plus the stoichiometric coefficient of 1 times the first squiggle for reaction 1, plus the stoichiometric coefficient for the second reaction times squiggle of 2, right? And so for A, the moles of A would look like the moles of A0. In this case, minus squiggle 1 minus squiggle 2, right? Because a little bit of A is going to reaction 1, a little bit of A is going to reaction 2. We don't know how many are there until we actually solve the problem. And so for a system like this, if I fill out the rest of these, N sub B0 plus psi 1, and N sub C is N sub C0 plus psi 2. I'm just making those up. Those are not the numbers that we need for that reaction. I'm just giving you an example here. And so each one of these, if you now want to know the total number of moles, it's the sum of all of those. which is the initial, what would this case be? That's it, right? There's no net moles of change here, but maybe there is a net moles of change. Maybe it's plus psi1 plus psi2. Right, I'm making those up. If you were doing the math the way that I've done it in this example, there would be no change in moles. And then each of your A sub i's that you need would look like Y sub I divided by, or sorry, Y sub I, which is moles of I divided by total, right? And so this looks like a big nasty function, potentially, of squiggle 1 as well as squiggle 2. And then those eventually get put into your product term of A sub I raised to the stoichiometric coefficient, which we set equal to K sub A, but there's two of those, right? There's a K sub A for the first one, and there's a K sub A for the second one. But it's the same set of ends, right? It's still this end, and this end that go into both of them, right? So it goes in here, each one of those, but it's exactly the same ends that go in here. And so you have a system of reaction, a system of equations, two equations, and the two unknowns that you have would be the squiggle 1 and the squiggle 2. Again, this is not the stoichiometry that we had. I'm just making those numbers up. So that's as close as we can get there. For the rate law problems, yeah, you can write them as forwards and reverse rates. That's fine. Or you can use the equilibrium constants. Brian, for the project, use the values that I gave to you. They're in the project statement. How do you set up the calculations for two reactions? I think that's what I just had. Lewin, the question about how to solve two reactions or two equations for two unknowns with F-solve, that is in section 1.8 in your book. Is the solution for problem 7 correct? To my knowledge, it is. Ever so conveniently, it seems like the questions have slowed down a little bit. It's about 4 o'clock. I will turn you all loose to work on your homeworks. Don't forget the quiz too. If you're working on homeworks, give yourself 10, 20 minutes for the rest of those. Would nu sub I be nu sub I1 for reaction 1? Yes. And nu sub I for reaction 2 is nu sub I2. Nu sub I, comma 2. Okay, I will, I'm just going to leave the meeting up for a bit, but I'm actually going to leave the meeting. And so you can hang out for a minute if you want to. Although actually, I don't think you can actually talk to anybody, so yeah. Okay. Good luck, folks. We will see you on Wednesday. Stay safe out there. Stop our recording. Stop our recording.